Lights, camera, action. Okay, so we're going to video here, and we're going to talk about the notes for exponentials. So what I am going to do is pull up this document here, which is on Canvas. So if you're doing this at home, you can go to Canvas, and this worksheet should be available. I've already got it on my computer, so we can see. Oh, wait a sec, I gotta go back to the camera. I didn't do that right. So I'm going to do this so that now the people at home can see the same thing we're seeing, hopefully. So I am going to fill this in as we go. You're going to need a graphing calculator. Now, I could show this here, but I don't think I'm going to try to do that. I will just talk about what I see on my calculator and make sure you see the same thing, because I haven't figured out yet how I can share the calculator screen on the video. So if I switch to there, I'm not sure if they're going to see anything at home. Okay, so anyway, we should be seeing notes for exponentials, and it's example 1, and you're going to invest $100 in the year 2000 at 5.5% annual interest compounded annually. So we have the year is 2000 and the dollar increase. So in the year 2000, there's not going to be no increase because you're going to have to wait till the end of 2000, or we're going to say maybe January 1st, 2001. So in 2001, then, since we're getting 5.5%, and that's going to be compounded annually, so we are going to get, how are we going to figure out what our answer is going to be? How much are we going to have then on January 1st, 2001? Help us out. Anybody? Oh, it's been a long summer, hasn't it? So we're going to get the $2,000 that we started with, plus we're going to get 5.5%, which is going to be 0.055 times that 2,000. That's going to be the interest that we're going to earn. But we're going to do a little algebra on that. So we're going to factor the 2,000 out because we're going to try to build on this here. And so that's going to leave a 1 plus 0.055. And so that's really going to be then 2,000, that's the amount we started with, our principal, times the 1.055. And if you throw that on your calculator, go ahead and do that. And so are you getting, like, what? Oh, hold on. The year 2000, I did that wrong. Back up. So it was the year 2000. We're investing $100. So I'm going to make that 100 plus 0.055 times 100. Sorry about that. So we're going to factor out the 100 times the 1.055. We could almost do that in our head, right? So we're getting then $105.50. So, and the columns don't show very much, but it says the amount here, and then it's going to say how much did it increase. So for that amount, and then I'm going to say increase there. So the amount would still have been 102,000, but we didn't get an increase. Now we've got $105.50 is the amount in 2001. You with me here? And that's going to make the increase be $5.50. Okay. Now here's where the compounding comes in. So now in the next year, in 2002, we are going to take that $105.50, and it's now going to earn 5.5% interest. So if we write it out, we're going to get that, again, the $105.50 times the plus, rather. So that's what we start with at the beginning of 2001, plus we're going to get the 105.50 times the 0.055. So we keep the balance, plus we add the 5.5% interest. You okay with that? Okay, so if we again now factor out this time the 105.50, leaving the 1 plus 0.055, then we're going to get 105.50 times the 1.055, just like we did before with the 100 times 1.055. But remember, this 105.50, that came from the 100 times 1.055. Right? So this 105.50 is really the 100 times a 1.055 times another 1.055 in year 2. Is that okay? Which is supposed to suggest exponential growth. So it's the 100 that we started with times that 1.055 squared. Okay? So, throw that on your calculator, see what the amount is, and see what the increase is. Richard, you just saving your batteries? Oh, you already did it. Nice. Anybody got the amount?
111.30
And how much was it?
30 cents.
30, sounds good. And so if you subtract those, the new increase is 580. So this is the compounding. So you can see that the increase in the second year is greater than the increase in the first year because the interest you earned in the first year is now earning interest in the second year. And so what we're getting is going to be exponential. And so in 2003, what is that going to look like? Can we jump to, it's going to be 100 times what?
1.055 to the third.
Nice. And you can do that in the calculator in a minute and get those others. And so in 2004, you're going to get 100 times
1.055.
Nice. So go ahead and do that, get your numbers there, and then find your differences, and we'll see if we agree on the differences. And you can use the exact values you get on your calculator, but when you write down your answer, since we're talking dollars and cents, let's just write down, round it to the 100, to the nearest penny. I'm going to just switch the screen here for the people watching this, if I can do this right. So they can see what we see. So there's the work we've got so far on the board. We've worked through what we were saying, but the people at home couldn't really hear. Here's our answers so far. So the difference, did anybody get the difference in 2003 yet?
612.
Nice, 612. And in 2004?
646.
$6.36. Nice. Okay, so we're in agreement. Okay, I'm going to go back to the document, hopefully. There it is. Okay, now so we're going to jump down to the formula. So after T years, now we're going to jump to kind of generalizing this. So we have this 5.5% interest, and we started with $100. So they're asking us for, shall we say, the amount A of T is going to be, what's that formula going to look like after T years?
100 times 1.055 to the 2.
Nice, exactly. So it's exponential. And I don't care if you use Y's and T's or X's or whatever, but that's the idea. So it's going to be A of T, I've got written, is 100 times 1.055 to the T. Now the ratio, the second question there is the ratio of values. So the idea is the ratio of values is if you look at the amount you had in 2001 divided by the amount you had in the year 2000. So 1.05.50 divided by 100 is that ratio. And then you can do the same when you take the 111.30 divided by 105.50. That's that ratio. And the same thing for the amount you had in the year 2003 divided by the amount you had in the year 2002. What is that going to be each time? Can you tell? What is it?
It's the 1.055.
Yeah, so that ratio is going to be the 1.055. That is because what we did each time as we were down, we multiplied the 100 by 1.055. And then we took that answer and multiplied it by 1.055 again. So when you divide those, you're going to go back and get the 1.055. So this is a characteristic of exponential functions, is that the ratio of successive terms is going to be the same. And we can see, we talked about this some last year, and that ratio is going to hold in it. So it's going to be a 1 plus r, where r is that percent increase. That's going to be the percent increase or decrease, because if this was a number less than 1, then that difference would be how much it is decreasing each time, the percent that is decreasing. Okay, we okay with that? Okay, stop and ask if I'm going too fast or something's not clear. So I'm going to move this down a little bit. So now we're going to say, in general, an exponential growth is given by p is equal to p sub 0 a to the t. What does the p represent there? Whew, just lonely in here sometimes.
Can you repeat the question?
Yeah, so we're trying to say, in general, this, can you see that? It's kind of small. Can you make that bigger? I don't know. Oh, I can definitely make it bigger. I don't know if I want to make it that big. That better? Can you see that? See if it's just a little bit more. I'll have to move it over. So in this equation, p equals p sub 0 a to the t, what does that p represent?
The amount after,
Right.
like your answer.
Yeah, the amount after what? Or I should say
T.
t years after 2000. Because that's what we said we were starting at. Is that okay?
Yeah.
You all right with that? Or do you want us to argue with Miranda? Wise choice. P sub 0, what does that stand for? Yeah, so it's the starting amount, which we usually call the initial amount, but starting amount works great. So it's the initial amount, how much we had at time 0. And the little a there is,
1 plus R.
yeah, it's I'm going to say first it's the base of the exponential, but you're exactly right. It holds in there that percent increase or decrease, so that a is equal to 1 plus r. And then the little t is,
Year.
yeah, it's the number of years, and in this case, in our particular example, it's the number of years after the year 2000, but that will vary from one problem to the next. Very good. Okay. Now, can I scroll this somehow? Oh no, come back. Dang it. Where did you go? There you are. No, I don't know how to scroll it. Where do I scroll? It's not being very cooperative. Can't grab it and move it. Oh, there we go. Okay. So now here's our example 2, and I'll blow that up for you again. So this is a new example. And so you've got, now here's the year 1998, 99, 2000, 2001. It's the population of the United States given in millions, and we're going to find the ratio. So what I want you to do here, this is kind of messy, the data, because this is real life, and that in real life is kind of messy sometimes. So you're going to, for the ratio, you're going to take the later year divided by the earlier year. So the first ratio you're going to get is the 279.3 divided by 276.1. Does that make sense? And let's go to 4 decimal places there. So 4 places past the decimal. So I'm going to just write up here, we got 276. You can go ahead and start working on those because I'm going to ask you those in a minute. I'm going to write it down here so you can reference it on the board. So 1998 is 276.1, 99 is 279.3, and 2000 is going to be 282.4, and 2001 is going to be 285.3. So when we do those ratios, we're going to take the 279.3 divided by 276.1, and to 4 decimal places. Anybody gotten that far? What do we get?
1.0116.
That's what I got too. Anybody not getting 1.0116? And then you're going to repeat that doing the 282.4 divided by the 279.3. And let's go to 4 decimal places there. Somebody other than Miranda, so let me see if somebody else.
1.0112 or 1.
Okay, good. 1, that's what I got to, 0111. Okay, 1.0111. And then we're going to do the 285.3 divided by 282.4. And somebody besides Garrett and Miranda can give us that one.
You got 1.010.
And then 3, I think, is that the 4th one?
Yeah.
Okay, good. So you can see they're not identical, but it sure is suggestive of an exponential relationship because it's so close. And so let's just, in this case, for no particular reason except it makes me feel better, let's just take the places where we have agreement. So those all agree to 2 decimal places. So we can use that then. Where do we write that? So it says to write an exponential model. So our exponential model is, we're going to say, should we say the population, P of T, of the United States is equal to, so what do we use as the starting value here?
276.1.
Very good, 276.1, because that's where our data starts. So our time 0 is going to be in 1998. And then what is the base of our exponential going to be?
1.01.
Yeah, and we're going to just take 1.01 because that's where we have agreement exactly. And then that's going to be to the t power. Make sense? Okay, now it says predict the population in 2010. So what next?
We put in 12 for
12 years.
T.
So yeah, since time 0 we said was 1998, and in the year 2010, that means our t is going to be 12. So you can, on your calculator there, put in 276.1 times 1.01 to the 12th power. And when you do that, let's round to, what did I do? Let's just round to the 10th place here. And as soon as somebody gets it, you can let me know.
311.1.
Nice, 311.1, and what's that going to be in?
Millions.
That's going to be millions, because our units here is millions. So the population we're predicting would be 311.1. What was our initial population? It's asking right here.
270.
That's our 276.1 million. And what is our growth rate? What would we say is our growth rate?
1%.
1%. Because that's good, because remember this is 1 plus R. So that 1.01 is 1 plus R, so the R is going to be how much more than 1 we have. That's 0.01, and so that is going to then become 1%. I'm trying to bring back my little R. Okay, and I'll blow it up again so we can try to see it. So example 3, now we have for each of the following, can we find the initial value and the growth rate? We're looking at example 3 on part A. So I give you a moment. You can try to jot down your answer, and you can turn to somebody. Can you see that? Maybe even bigger.
Just a little bigger would
A
be
little
nice.
bigger would be nice. Okay. Is that legible yet? Bigger still. I'm going to run off the screen here. So it's P equals 27.3 times 1.023 to the T power. Oh, we have a visitor. Hi.
I was wondering if I could install a sound system for your room so you could have a microphone to,
I think I have one there.
the one that comes with the school system doesn't work.
Oh,
It cuts out all over the room, so we've been installing better
that
systems.
would be wonderful.
Okay, thank
Oh,
you.
you bet. Okay, so had enough time. What is our initial value? 27.3, because that, if you put in 0 for the T, then you're going to see it's going to be that 27.3, because 1.023 to the 0 power would just be 1. That's going to be your value. And the growth rate is going to be, can you tell what that is? Nice, 2.3%, because 1.023 minus the 1 is 0.023. And if you change that decimal to a percent, it becomes 2.3%. Okay, how about the second one? What's the initial value?
19.7.
It's 19.7. And can you see, what is the growth rate going to be there?
-9%.
It's a negative 9%, exactly. So we have that 1 plus R is equal to the 0.91. So if you subtract 1 from the 0.91, you're going to get a negative 0.09. And then when you make that into a percent, it's a negative 9%. So it seems weird to say the growth, but the growth is negative, or you could also say it's decreasing by 9%. Very good. Okay, how about, can we try that example 4? So suppose Q equals f of t is an exponential function, and I'm going to do this one with you. F of 20, it's been a little while. So we've got f of 20 is equal to 88.2. And we also know that f of 23 is equal to 91.4. And we are going to try to find what is the base and what is the growth rate, and then evaluate what is the value of that thing at 25. Okay, remember how to do this? Kind of. So we are, should we just make our life easy and say y equals ab to the x? Should we use that as our base function? Is that all right?
Yeah.
Or should we use, I guess they use q's and f of t's. You okay with just y's and x's, or you want to,
No.
you're okay with that? Okay, so we have the 20 is going to be a value of x, and the 88.2 is going to be a value of y. So that's going to become 88.2 is A, we don't know, B, we don't know, and the x is going to be 20. So we're trying to figure out the A and the B. Since there's two things we don't know, we need a second equation, and that's the f of 23 equals 91.4. So we're going to say 91.4 is A, B to the 23. Okay, so far. So coming back, Mickey prep students anyway? Tim's nodding yes. What do we do then? Tim, would you remember?
Don't you like subtract second equation?
Not subtract, because we want to get rid of this A.
So
Divide.
So divide. And can I just, I mean, we could do it this way, but we're going to get a negative exponent. So just, and there's nothing wrong with that, but it might be a little easier or cleaner. I'm going to put the 88.2 equals AB to the 20th underneath the 91.4 equals AB to the 23rd. Now if we divide those, we're going to get a mess on the left side, but that's what we got calculators for, right, to clean up the mess. But on the right side, the good news is we get rid of the A's, because they're going to divide out. And now we can use our property of exponents. B to the 23rd divided by B to the 20th is B to the 3rd, because we just subtract exponents. And now, messy though it may be, to get what the b is, our base, we are going to have to do what? No, not the log. Logs is when we get the variables in the exponent. But here the variable is the base. So how do we get rid of this 3? Either cube root or to the 1/3 power, either way. So I'm going to write it as a 1/3, but cube root is exactly the same thing. So we're going to take that quantity 91.4 divided by 88.2, raise it to the 1/3, or do the cube root. And now we need all the decimal places of accuracy, but can somebody tell me what they've got to 3 decimal places?
1.012.
1.012, does that sound right? Do we get agreement? Okay, now, we're not going to compute using the rounded answer, but we'll write that down because we wanted to find the base b, and we just did that, 1.012. Okay, and then we can answer the question r. What is the r? The percent increase is going to be
1.2%.
1.2%. Very good. And now we can find, oh, well, not quite yet. We want to find f of 25. So that means we need to know not only b, what else do we have to know? We need to find the a. Okay, so now should we use the one that's got the 20 exponent in it? So here we can say the 88.2 is a, which we don't know. The b, which is, I'm going to write 1.012, but don't use 1.012. You're going to have to scroll down, capture that, all the decimal places of accuracy, and then we're going to raise that to the 20th power. You with me here? I need nods of heads. Okay, Evan, are we okay? So we're going to divide that to the other side. So we have a is going to be this 88.2 divided by 1. And I'm writing down 1.012 to the 20th, but do not use the 1.012. Don't use the rounded version. You understand what I'm saying? Anybody not know what I'm saying? To go down and capture all the decimal places of accuracy and raise that to the power. Tim, you want to see it done, or you?
No, I don't.
You got it. Okay. Evan, we okay? Okay. So then, now once you get that value of a, after we've computed with all the decimal places of accuracy of our b, now you can round your. No, we don't want to round it. Yeah, we can round it because just so I can write it down. So tell me what that is rounded to 3 decimal places.
69.548.
548.
Yeah.
So we now have then y is equal to that 69.548 times the b, which we said was 1.012, raised to the t power. So the f of 25 is going to be, we're going to plug in the 25. But remember, we're not using the rounded answers in our computation. Okay, so use all the decimal places of accuracy. After you've done the computation, then you can round your answer. And let's see if we agree.
Uh, 93.598.
I love it when we agree. 93.598? I'm going to just show, I think, real quick here the board, so anybody that's at home looking at the video. So there's our work, and they can pause it if they need to try to follow all that. And then I am going to go back to where we were. I think I did that right. Okay, now we're going to look at, we have y equals, so y1 equals 2 to the x, y2 equals 3 to the x, and y3 equals 5 to the x. I'm going to make that bigger for our visually challenged. So when I say, and like I have on this document, on the window -5, 5 and -2, 5, I'm telling you on your calculator to choose the x min and x max to be negative 5, 5, and the y min, y max to be negative 2 to 5. So when you do that, you'll get kind of a nice graph and see what's going on there. If you have one of those newer models, like Miranda, that graphs in different colors, it's so cool. So I'm going to try to duplicate what you should be seeing there here on the board. So I'm going to draw my axis in white. So I'm going to get something that looks like this. And then I'm going to go with the y equals 2 to the x is going to be in purple. And so the idea is when x is 0, 2 to the 0 is 1. When x is 1, 2 to the first is 2. When x is negative 1, 2 to the negative 1 is 1/2. And we're going to get something that looks like that. So there is my best 2 to the x graph. And I'm going to do pink for y equals 3 to the x. That's our second one. So again, when x is 0, we get 1. But when x is 1, we're going to be up at 3. And when x is negative 1, we're going to be at 1/3, which is smaller than 1/2. So it's going to be below. So I'm going to get something that looks like that. So we should be seeing then that on the y-axis, they're equal to each other. To the right of the y-axis, my 3 to the x graph is above the 2 to the x graph. So it is growing bigger, faster, the 3 to the x than the 2 to the x. But to the left of the y-axis, the 3 to the x graph lies below the 2 to the x graph. So it's getting smaller, faster as you go to the left. And then I'm going to do y equals 5 to the x in orange. So again, at 0, we're going to have 5 to the 0 is 1. At 1, we're going to be up at 5. And at negative 1, we'll be at 1/5, which is smaller than the 1/3, which was smaller than the 1/2. And so we get something that looks like that. So the way I think of it, I don't know if that helps, but with an exponential, the bigger the base, the closer to a right angle it tries to be. Now, it's always going to be a curve, but you can see that to the right of the y-axis, the bigger base exponential gets much bigger, much faster. And to the left of the y-axis, the larger base exponential gets much smaller, much faster. It hugs the y-axis faster, the x-axis faster. All right, so we got it. So now answer the questions here. For what values of x is 2 to the x less than 3 to the x less than 5 to the x? Where does 2 to the x lie below 3 to the x, which lies below 5 to the x? For what values of x?
Greater than 0.
Yep, x strictly greater than 0. And for what values of x does it go the other way? That the 2 to the x graph is bigger than the 3 to the x graph, which is in turn bigger than the 5 to the x graph. Less than 0. And then part C, where are they all equal to each other? Just at 0. They're equal to 1, but that's at 0. Okay, so I'm going to talk a little bit about concavity. It's been a while. Let me slide down a bit here. And I'm going to just quick show, I think, the camera again for those that are watching this at home. So you can see, and hopefully you can see the color there. This is our graph of 2 to the x, 3 to the x, 5 to the x. And this is where the 2 to the x is smaller than 3 to the x, which is smaller than 5 to the x. And this is where it goes the other order, and this is where they're equal to each other. All right, hope you're not getting whiplash as you're watching this. And we're going to go back to our notes. Now, we talked about concavity a little bit. So a function is concave up. So there's a couple ways you can think of this from what we learned last year in AP Prep. And we're going to learn some nice calculus ways of determining what's going on here. But concave up, so is that what I said first? So concave up. So F is concave up if, and we're going to say, I'm going to say the words bowl-shaped up. Bowl-shaped up. So a function can be increasing in concave up, something that looks like that. It can also be decreasing in concave up. Okay, so the increasing decreasing is totally independent of the concavity. Okay, these two graphs that I have here are both concave up. Now what we talked about last year in AP Prep so that's kind of a nice visual description there, bowl shaped up. If you look at, I'm going to draw two segments there on the first graph. If you look at the average rate of change, which is the slope of that line joining those 2 points, and I'm going to switch the screen back here for a moment, because I would like them to see this. So here is our first example of a function that's increasing concave up. There is decreasing concave up. Now, in the pink here, this rate of change, average rate of change, is the slope of that line. And then the average rate of change here is the slope of that line. How do those slopes compare? Is this, as we go from left to right, are these slopes getting bigger or getting smaller? Bigger, right? Slope might be like 1, maybe that's like 3, so it's gotten bigger. So we would say that the rates of change are increasing in this curve that is concave up. Okay, so I'm going to say the rates of change, that's ROC for rates of change, are increasing. Now let's look at the second curve. So now here's our yellow curve over here that's decreasing, but still concave up because it's still bowl shaped up. So as we look at the rates of change, as we're talking about the slopes of the lines there, those lines right there. So the first one is a big negative slope, and the second one is a smaller in magnitude negative. So maybe this is like -4, and this is like maybe -1/2. So when you go from a big negative to a smaller negative, is that increasing or decreasing? It's increasing, right? Because you think number line, -4 is to the left of -1/2. So as you move this way, you're getting bigger numbers. So it stays consistent that in both cases here, where the curve is concave up, the rates of change are increasing. Does that make sense? That's an important idea. Okay, now if F is, and I'm going to show it symbolically, is concave down, and don't get your feelings hurt here, that's concave up. Okay? I'm not saying FU, that's F is concave up, read it correctly, it matters. This is F is concave down, okay? Now, if we can be increasing or decreasing, be concave down. So here is a function that is increasing in concave down, and here is a function that is decreasing in concave down. So increasing, decreasing is a separate issue from the concavity. So we would say a function is concave down if it is bowl-shaped down. Bowl-shaped down. That's what we mean by concave down. So there's a visual. So that's a description of what the graph looks like. Now, we can also talk about here the rates of change. So when you look at, a line segment joining 2 points on the curve there, compared to a line segment joining 2 points on the curve a little bit further down to the right. Now, the slope of the line here, that's the rate of change, the average rate of change, compared to the slope of the line here, the average rate of change. Is that getting bigger or getting smaller? Smaller. So we get that the rates of change are decreasing when it is concave down. And similarly, we're going to say that, see that with the negative slopes. You just got to think about it a little harder when it's negative because it's a little counterintuitive. So that might be a slope like, say, -1, and that might be a slope like -5. But -5 is smaller than -1. So as we go from left to right, the rates of change are decreasing. Good to go? Very good. Okay, I'm going to go back. Hang on there, people that are watching. We go back to our note sheet there, and so we have, and I don't know why it looks so goofy like that. If f of x is a to the x, then how does the graph of 1 over a to the x, which is y equals a to the negative x, compare? So the question is a to the x and 1 over a to the x, which is also known as a to the negative x. How will their graphs compare?
Will do be flipped over that.
Yes, exactly. So they're going to be flipped over the y-axis, or we would say reflected, reflections in the x-axis, in the y-axis. You got it, right? Okay? Okay, just a little refresher. We're going to slide down, and now we have this thing here. I'll blow it up. So now we're looking at y equals 2 times 3 to the x minus 4. Y equals 2 times 3 to the x minus 4. So the question is, can you predict the asymptote, the y-intercept, the domain and range? Should we walk our way through it? It's been a little while.
Sure.
Yeah, that's what I like to hear. Okay, let's go with purple here. So first, let's look at y equals 3 to the x. I'm going to switch the screen again, I think. So we'll come back here. There we go. So here we are looking at y equals 2 times 3 to the x minus 4. So first, y equals 3 to the x. Because the base is bigger than 1, it's going to be a growth curve. And so it's going to have just a basic shape, something like that. Okay? Then if we add in the 2 times 3 to the x, what does that 2 do? Am I almost out of time?
Oh, is it 2 to?
Yeah, it's actually not a shift, it's a vertical stretch. Every y value gets multiplied by 2. So in particular, this one's going to be at 2. Each of these will be 2 bigger, so it's not any longer exactly the same shape. Does this class get out at 1:30? Oh, time flies. Okay, I'm going to run out of time, so I want to make sure. So I didn't get all the way through this, but on your support materials on Canvas, there is a Khan Academy style video that will finish up what I wanted to do here. You can try to finish this exponentials thing on your own, this is available on Canvas, and then you can check your answers there because I go through it. But that's separate from homework number 3, which you still need to do today as well. Oh my gosh, piled on to the homework 2 that you didn't do yesterday. Okay, I'm going to stop this thing.